We present deforming radiance fields with cages, a simple yet effective approach for radiance field deformation. In this work, we focus on the deformation of the neural radiance field, or NRF. NRF recovers 3D scenes from posed multiview images and allows photorealistic rendering. However, conventional NRF can only model static scenes. In follow-up research, some methods extend NRF to support dynamic scenes. However, these methods can only represent the captured dynamic scenes and do not support the reanimation for the novel scene synthesis. While some works focus on human bodies or articulated objects, these methods not only model the input dynamic scene, but also create novel scenes by skeleton manipulation. However, these methods are only suitable to specific categories and difficult to be extended to arbitrary object categories. In this work, we propose a new algorithm to enable the deformation or animation of radiance fields, which can be used for arbitrary object categories. Here is a high-level overview of our method. Unlike the previous methods which use dynamic scenes as input, our method uses a static scene as input. After radiance field optimization, we extract the mesh using Marching Cubes algorithm.
And then, we generate a coarse mesh called cage that encloses the scene.
Finally, using this cage as an interface, our method can achieve the deformation of the radiance field by controlling the cage vertices. Our method focuses on the deformation of the radiance field. The rendering process of the radiance field includes ray casting and sampling, color and density computation, and volume rendering. The core part of the radiance field is such a continuous representation, which maps position and view direction to color and density. This work studies the deformation that could be applied to such a continuous representation. Our method uses a coarse mesh called a cage as an interface. Cage-based deformation is not new, and has been widely used in the deformation of fine mesh. The basic idea of cage-based deformation is quite simple. Given a fine mesh and a corresponding cage, for a vertex x of the fine mesh, we compute its cage coordinate, which represents the relative position of x inside the cage. After deforming the cage to the desired shape, we can use the cage coordinate to calculate the deformed position of x. Applying this operation to all the vertices, we can get the deformed fine mesh. An important feature of cage-based deformation is that the cage coordinate for x is continuous in 3D space, so the representation of such deformation can be naturally extended to the radiance field. Suppose we have obtained the optimized radiance field and the corresponding cage from multiview images. We control the vertices of the cage like this for cage deformation. What we want to know is how to render the deformed scene that corresponds to the deformed cage. As a first step, just like the normal radiance field, we shoot the rays. And then randomly sample points on the ray. Since the color and density of these points are unknown in the deformed scene, we use cage-based deformation to map their positions to the original scene and compute the corresponding color and density values. By applying this operation to all the sampling points, we can obtain this kind of deformed ray with known color and density values. Then, by volume rendering for the deformed rays, we can get the RGB color of all the pixels. Given the view-dependent property of the radiance field, we not only map the position of the sampling points, but also map their view direction. Please refer to the paper for details. The left side are the original scenes, and the right side are the deformed scenes. Our method also works well for the real-world scenes. Also, our method can be applied to the object movement in the radiance field. The only thing needed is to create a simple cage like this one, and move it. Finally, we show some failure cases and limitations of the proposed method. First, some artifacts will appear when the under-modeled parts are exposed after deformation. Second, while this is an issue with cage-based deformation, larger deformations may result in implausible rendering results. Also, the cage-based deformation is computationally intensive, and does not support real-time deformation and rendering. A faster cage-based deformation algorithm may be a promising direction for the future work. Thank you for watching. Please also check our project page.